Hello, class. Hello, class. I am so sorry for coming to you with this video a little later than planned. I got tied up, super busy after we got out of class on Monday, and then swamped Tuesday, and it just completely slipped my mind. But I'm coming to you today to actually look at 3.1. Wanted to make just a short video where we kind of talk about a few things and I try to look at some problems. And yeah, so we'll get started. I am going to have to share my screen a few times here. Let me turn my phone on silent. My apologies. Okay. So we're talking about 3.1, which is the derivative and the tangent line problem. So here we look at point. Period problem. And these four major problems are divided separated by three. We've got the derivative of each problem involves what does it mean to say made a problem of the tangent line. You can approximate excuse me, um, as we what we're doing is the essentially precast, but now so when we think about flow, think about it. When we look at it, well, we're going to apply that thinking about finding when we evaluate, it can be called another natural law. So we will find the time the difference that second along the secant line or yeah, so let's say first point. Second point, looking at a distance. And an F at. So you can say that this is 1, and this is 2. Okay. So when we think about finding flow here, we look at the change in the function at that second point. So we'll look at that value, I should say. minus the function value at the first point over changing the second x. But when we simplify that bottom, okay? So the right-hand side of this equation is called the denominator delta x, whereas the numerator is y, which is the function minus the function. And you can look at it how we can decrease delta x because you get more and more accurate approximations of the slope of the tangent line closer your points are to each other. Okay, so the more that you can reduce that delta x, the better your approximation will be for your slope of your tangent line. So in other words, as delta x approaches 0, as we increase that delta x value, get a better, more accurate approximation for that tangent line, for that slope of the tangent line. So that brings us to the actual definition of the tangent line with slope m. So it is, and it's just applying the quotient, like applying the limit to that quotient. Remember right here, that difference quotient. So we form the definition of the tangent line when we apply the limit as delta x approaches 0 of that difference quotient. That becomes our slope. So as we reduce delta x, as we reduce the difference point, that value equals our slope. Okay? And of course, I'm going to do some examples. So that was one of the most important things I really wanted to look at. And then that even takes us further into the derivative of definition of the derivative of a function. So that limit of the quotient is just our derivative. So when we take the limit of this difference or changing x, changing y over changing x, that is our derivative. So the limit used to define the slope of the tangent line is also used to define one of the fundamental operations of calculus, which is differentiation. Okay? So the derivative can also be used to determine the instantaneous rate of change, the rate of change of one variable with respect. That's why they're equal. Remember, instantaneous rate of change, slope of the tangent line is equal to the derivative. Or the same as the definition of the derivative. Okay. I do have several examples I know that I have planned on working in class, but I think I'm straight into examples and just go from there. That way you are in your assignment. So I'll look at that. Before we do that, I wanted to make sure I mentioned something, continuity as well. So keeping in mind the derivative, it says the alternative limit form of the derivative is useful in investigating the relationship between the differentiability or between differentiability and continuity. The derivative of f at c, okay, is equal to the limit as x approaches c of f of x minus f at c over x minus c, provided that the limit, of course, exists. So this is just an alternative form of the derivative, in other words, okay? Where we remove the delta x and instead we say the limit as x approaches that constant c. Note that And as x approaches c to the right, those values have to exist. And the limit, right hand and left side limits, and left and right side limits have to exist, and they have to equal. Okay? These one-sided limits are called the derivatives from the left and from the right, respectively. It follows that if f is differentiable on the closed interval AB, and it is differentiable on the open interval AB, and when the derivative from the right at A and the derivative from the left at B both exist. So it is fully differentiable when it is differentiable on the open interval, when the derivative from the right at A, so coming towards A from the right, and the derivative from the left, coming towards B from the left, both exist. When a function is not continuous at x equals c, it is also not differentiable at x equals c. Okay? So that's just how differentiability and continuity relate. If a function is not continuous at some point, then it will also not be differentiable. And then I put the step function up there to just kind of illustrate an example. The greatest integer function, also known as the step function. And this is basically your step up as you reach that next integer. Right? Take a look here. Look for the one, okay? And then when we approach from the side, 0. So the greatest integer function is actually not different. Okay. All right. Another example in the note. Function where you've got x minus 2, or an example of an you got x minus 2, then after that it says below here, it has no break, it has no gap. So in this case, it is continuous, but note that it's not behind. So whereas we can stop, but the left and right side limit and one side are not the same. So therefore it is not equal. Okay? So x is not different as equals, and from the right are not. Okay, that makes sense. And when I say derivative, I'm referring to the slope. So from the left side, the slope is actually negative, and the right side is increasing. Okay? You could evaluate that. I want you to take the line is going down, and from this remember, derivative is the slope. And then you can actually look at the limit. You can actually, that's not just looking at the one side. to minus x, right? So hmm, yeah. So when we look at it from top, the absolute value that we have minus zero. Although you've got absolute value symbol on this left side, we're actually using value x or small that you look at it. Now on top, absolute value bottom is where okay, because you're on the left side and you're going to be substituting in values that are less than 2. So for example, like 1.9 something really, really close, but that would yield a negative there. So you subtract. So that's how you end up. Whereas here you're approaching at the right side, you'll be plugging in something larger than 2, maybe like 2.1, and you would end up with a positive 1, a positive slope. Okay. Okay. So that means that reverse is not always. Continuity doesn't always imply different steps, which is um, but it was not differentiable. There won't be a whole lot of those problems like that, but that is one of them. So while differentiability does imply continuity, the reverse is not true. Not automatically imply differentiability. Okay. So let me just take a look at maybe a few problems here. Just to kind of, this first one saying so your whether greater this number two asking you to find. I remember he listed order one. The ID for this question is 6.10, but it's just like find the slope of the tangent. Well, you've got the function itself. So anytime it's written in terms of mx plus b, the slope is the value that's in front of the x. Okay, so there's really not much to say there. The function is a line, and the slope, therefore, is that 7/5. Now, the next problem, number 3, says find the derivative of the function by using the limit process. First of all, whenever you have a constant function, the derivative of a constant is automatically 0 because slopes that are equal. But Um, and it actually works. This is how many algebraic linear function. Okay. Look at it. All of those your slope is 7. But it really is. But we have although the process, so this would be the S at X minus the function over. Remember? So a function at where I have X plus, and then I've got minus, and then I've got the original function. So I have 7, where I have 7 X minus over delta X. This delta, I'm going to simplify here. I'm going to simplify the S. I've got 7. Here I'm subtracting F at X, that minus okay. Look what's going to happen here. 7x, 30. I'll end up right now uh, delta x uh, 7 over delta. Okay. The delta x on top cancels with the delta x on bottom. I'll end up with, screw that up, end up with the limit of delta x bottom up. And the limit of a constant is just that there is delta x statement in this expression. Constant. Delta x is not affecting that constant. Okay? And that's a really pretty simple example to process on. That one. We can get a bit more involved. Here's another one. The computer's going to know or image doesn't be uh, properties that will apply, that will make this, but because this is, we don't have to use the limit process. All right, now this one I am clear on it. So I want to work. This is going to be the main one. I want to make sure I work. Ooh, that's a good one too. Yeah, many of these would just take you doing a little work with them. Not terrible, but a little bit of algebra techniques, a little tedious, a little bit. You may have to rationalize a little bit. So a couple of them can get a little bit involved. So I'm trying to see if I need to do a different one. I'll go ahead and do this one. So we take the function as x, delta, and x blurring. And then we have minus function. Require a little bit of simple. So right here, find f of delta. And I have minus f of x, a minus left off. Okay. So yeah, I'm gonna have to clean this up. So your algebra techniques will, okay. If you had a rational expression, if you had a radical in a denominator or something, you would maybe have to put in there you need to have it because you don't have it. You have to rationalize, and that's multiply top and bottom by the conjugate. You're gonna have to recall some algebra. Okay. Look at the textbook also. Lots of examples in there. Even if the videos don't show it, look at your text. Look at examples. May require more algebra. It's gonna require the answer. Got got my got, got my editor. Now got my okay. That ends up giving me something. Okay, let me zoom out. All right, so that's what I have alone. So I'm gonna bring it as equal to x. Then I've got x right there. I wrote that down. So that's where I know. I'm going to bring down what the getting rid of the parentheses and the plus 4. That was plus, so that was plus, that was minus. And that's, yeah, I'm going to clean this up. There's nothing going to keep back, okay? So look, it's with the minus, okay? Minus 4 cancel, and then your plus minus 8. So it looks like it's got the delta x uh, 2x plus delta x plus delta x. So everything that was x delta x and then delta x is all over delta. Okay? I know it's a lot. Guess what? After we get past the limit process, we'll get it and you will not have to do. Okay? I kind of want to show you now. I'm going to show you Monday, but I want to look at it, but it's actually in the which is put on the approach is using the limit. So remember delta x is approaching 0, but before I do that, before I actually take delta x to 0 and simplify, let's see if we can do some canceling out. Because I've got delta x in the top that can pull out or factor out so that I can make shift with the delta x. If I let the denominator approach 0 here, then that would mean the limit doesn't exist. So I'm going to see if I can do some limit. Delta x. When I pull out delta x, and when I pull out delta x, take a look at what's delta x is what's delta x. Well, guess what happens? We actually apply the limit. This approaches 0. So the limit of delta x approaches 0 or 2x plus 1. Yeah. That is the derivative of that function. Okay? Do practice, do look at your book for more examples. We this whole limit process, but I promise the work is shorter. Okay? We actually do problems that are not as long or don't require the limit process. Okay? Let's see what else we got. The rest of them. Let's see here. Let's look at this one. The derivative of the function using the limit process. Minus. Okay. So I'm going to take that function. Three over x plus minus, and now I have minus x minus. Okay. All right, and then I have delta. Okay. So this looks really yucky. Basically, you got a fraction. What we're going to do is Because once less is the fraction up in the bottom by our LCD, by the become the LCD or the LCM of our denominator, become multiple of our. So you've only got these two denominators, and unfortunately they're not. So the LCM on the top side is minus 9. I'm going to multiply the bottom by this. So top and bottom divided. So this is where those algebra come into play here. So what's going to happen so that you can clean this right now? So what's going to happen? So the let me just write it out. Minus 9, and then -2 does x. So it's a lot with the limit process. I'm not going to keep it. But again, it's the formula. So what's going to happen is all denominators with 3 times. We got minus 3 times x plus delta x. And then minus 9. And that's all delta x minus 9. Okay? So yeah. All right, so we got to keep on simplifying. So we are going to use the problem. I'm going to distribute here. Okay? And I still have this denominator. You may not worry about cleaning that. So I've got 3 minus 3 delta plus 1 minus 3. So that's negative. And I still have okay. This is cancel. Minus 3. Minus 27 plus 27. Right now, that's the limit. That's negative 3 delta x over delta x plus delta x minus 9 times x. Now this seems like a lot. So what's happening here? Delta x, delta x. Right now, we now have the limit 0, we got the negative 5, we got x plus delta x minus 9, and we got x. Okay? Now I can take 0 or I can apply the limit now. So what's going to happen is I've got plus 0, and then here I've got, so basically we let the delta x, I just have the 0 there. I'm going to just get rid of it. 3 over x minus 9. That is a lot to do, I know. But just keep working. Like I said, please look at your textbook for more examples. I am going to see if I have any other videos that I can possibly send you to, any other videos showing the limit process to different examples. I'm sure. But I will send y'all this link and I will post it on my YouTube channel. All right. Hope this helps. Bye-bye.